Hey everybody, let's talk about this new paper, Materials Maturity Levels. What are those? It's a systematic approach to evaluating materials development. This paper comes to us from lead author Anthony or Tony Rollett and co-authors Brinkley, Dimotakis, Graham, Pugliano at a variety of institutes. We got Carnegie Mellon, Institute for Defense Analysis, Caltech, Maryland, the Pentagon. So there's actually some cool people coming together for this. Now, what is materials maturity levels? Well, first off, it builds off of some things that you've probably heard of before. For example, you've likely heard of technology readiness levels, TRLs, right? From going from TRL 1 up to TRL 9, right? When academics write grants, sometimes they only want it to be in a certain range when they're willing to fund it, for example. This came from NASA in the 70s. It basically highlights the progress from an initial innovation trigger all the way to technology demonstration, integration with the system, integration in actual operating environment, right? And you've probably also heard of manufacturing readiness level, which basically tells you it's a similar process, but for how we manufacture things. Well, materials maturity level is sitting somewhere in between these two. The authors point out that there's a number of reasons why you'd want a specific materials maturity scale as its own concept, apart from the TRL and the MRLs, which are fantastic, right? First off, they point out that new materials often enable both new applications and engender new advances and capabilities in existing ones, right? They point out that very often new materials don't just have a single property, but they rather satisfy a full range of requirements for some given application, and that you have to consider manufacturability of that material at some given scale. And they point out this great sentence here that in an ideal world, applications provide then the pull for new materials, but then they have to be developed in time to allow for the final stages of maturation and application development. So let's take a look at these. The materials maturity levels go from 0 up to 5. 0 is a theoretical concept, meaning maybe DFT or some first principle calculation showed that a material could exist or interesting properties could be found. Then materials MML level 1 would be, let's show that the material actually exists experimentally, but probably at a lab scale. MML2 would now be demonstration of the properties. Maybe you measured enough of the material's property that you now believe that it could be scaled up to the point where you get to MML3, where you do a laboratory or a limited application of this. Then it goes to 4, where you've reached an industrial scale application, all the way up to MML5, which is that the material is fully accepted. One of the great things about this paper is they have a number of interesting sort of case studies or demonstrations where MMLs either could have shown that something was going to work or that it wasn't going to work. For example, they talk about boron arsenide. This is a material they point out that never really reached that maturity level for it to be used, even though it was originally identified as a promising candidate for electrical insulation and high thermal conductivity. So think of like electronic packaging. It needs to be, the substrate has to be electrically insulating, obviously, but you want it to get the heat out, right? So this could compete with even diamond, they thought. But when they actually went through the process of developing this and tracking its maturity, eventually found that the largest crystal that they were ever going to be able to grow was basically 1 millimeter, which was not going to be big enough for heat sinks. So an example, something that was progressing towards maturity level, but ultimately stalled. There's lots of other great case studies and analysis in here. I kind of like this one where it shows the TRL levels, the manufacturing readiness levels, and then where the MML levels would sort of fit in between these. And then they have a lot of cool things to say about co-design, right? Because obviously the way that you actually manufacture a part, as they point out here, whether it's casting, forging, 3D printing, sputtering, whatever it is, that's going to influence the microstructure and its properties. So it's a bit of a chicken and egg that you have to solve these things together and not just one versus the other. So it moves the design process from the linear process, which we see with the TRLs, to a more evolving co-design process, which is going to be inevitable in materials maturity levels. So check this paper out in the latest issue of IMMI.